What is linear algebra? Linear algebra is actually a subset of abstract algebra, which I'm going to be talking about today. So even though this course is called linear algebra, we really can't have a meaningful discussion if we are not speaking the same language or if we do not understand each other. Because in the context of linear algebra, we are going to use certain words, certain terms, and unless we know those terms, then we're not going to make much progress. Now, where do we find the definitions for those terms? Abstract algebra. So they are part of each other. Okay, linear algebra, like I said, is a subset of abstract algebra. In other words, if you learn abstract algebra, you're on your way to learning linear algebra. Now, in this course, there are two major components. There are two things that we are going to try to cover in depth. The first category is the systems of linear equations. One of the very impressive things in linear algebra is that it gives us techniques for solving multiple equations at the same time. It allows us to find the roots of multiple equations at the same time. Why is that important? Well, and what's the point of what's so important about finding roots of an equation? I think I'll come back to that answer once we go to Markdown, because I want to show you some math expressions. Okay, but equations, which can sometimes stand for models, and I hope you know that models are how we mathematically represent something in the real world. By finding the roots of an equation, and if that equation happens to be a model, we would have found the essence of that model. And with linear algebra, we're able to do this for a sequence of equations. So that's the first part. Okay, again, like we always do in every session, we start at the high level and then delve deeper, right? Because we want to have a picture of the discussion. The second part is matrix operations. This will be the bulk of the course, and for that matter, this encompasses the bulk of any linear algebra course. So I'll tell you what the subsets are, like what roughly goes into each category. But here are the major components that will be covered in both categories. Systems of linear equation, like I said, allows you to, or are the set of techniques that allow us to solve multiple equations at the same time. And we will achieve this by performing arithmetic operations on multiple rows. And what we want to do is eventually get to something called reduced echelon form or reduced row echelon form. Another part of another thing that we will learn is LU decomposition. The lower triangle, upper triangle decomposition. And when it comes to matrix operations, we have a set of special types of matrices. A very important one is the square matrix and the diagonal matrix. These types of matrices, especially the square matrix, is going to be very central to the entire course, because square matrices have applications in neural networks, in statistics. If you've heard of things like covariance and correlation matrices, they have applications. Principal component analysis, which is let's say our what's the word I'm looking for? It is where we are headed towards. So, and actually, it's this slide that I want to come to. So, principal component analysis. Now, it's not easy for me to go into PCA, at least not just yet. But if we are able to find the principal components of a matrix, that's a big deal. We can do things like pattern recognition, whether it's from pictures or tabular data or sound bites. It is used in stock price prediction. So if any of you are interested in quantitative finance, PCA is again a very big component of quantitative finance. Optimization is a subset of linear, or a superset of linear program, which we'll also talk about today. But PCA will give you a powerful ability in many different domains that concerns data. Now, in order for us to even be able to comprehend how PCA works and how we are able to extract the principal components from a matrix or from our data, we have these layers of prerequisites. So for example, PCA is a subset or a subtype of singular value decomposition. So in order for us to understand PCA, we must understand what SVD is, generally speaking. And the prerequisite for understanding SVD is knowing something called a characteristic polynomial, the determinant function, from which we can extract eigenvalues and eigenvectors. I have a good sense most of you have heard of eigenvalues and eigenvectors. Okay. And of course, we can only extract eigenvalues, eigenvectors, or rather we can apply determinant function to only a square matrix, which is one of the many matrices that we will encounter, but perhaps the one we will focus mostly on. So if you were to pick up a book on machine learning, on linear algebra, or if you were to come across a blog and you were to try to make sense, what is the formula of PCA, you would get stuck. At least I did. And then I had to figure out the prerequisites. And this is what it looks like. So the point I'm trying to make is, in this course, we're going to learn linear algebra with the goal of eventually understanding techniques like PCA that will then open these opportunities for us, to apply to many kinds of problems in the real world. Okay, so as opposed to just learning these topics in abstract, in an abstract manner, we want to see how every single concept applies to practical problems, and we will do this with Python. So you will implement some of these. We cannot implement all of these techniques with Python. So, for example, we can implement the determinant function in Python. Characteristic polynomial is a little bit more